morning, good afternoon, everybody. Welcome to our Friday HSM Hangout. My name is Jordan Roberts. I will be your host today. We have some really exciting stuff for everybody. We've got Tim Paul, application engineer with the Autodesk CAM team. We've also got Rob Lockwood. Rob is an HSM customer. He works for Oculus in his day job. He's going to walk us through some really advanced functionality inside of HSMWorks. Really quickly, before we get started, I just want to ask a couple of quick questions to understand where everybody's at. I want to know what kind of CNC machines everybody's running. So the faster you get your votes in, the faster we get back to the technical piece of today's portion. Tim, Rob, any thoughts? Are people running Haas, Bridgeport, Tormach? What do you think?
I think Haas is the easy choice. Maybe Bridgeport second.
All right, well, let's see what we got. And close the polls. Share the polls. Look at that. Boom. 70% Haas. That is awesome. All right, let's add a couple more in here. Now I want to understand, how long have you been using HSM products? I'm talking about Inventor HSM, HSMWorks for SolidWorks, Fusion, that's HSM in the cloud. Let us know. This is really great because what we're finding is that we're seeing a lot of people come back and join us week over week. So here, let's see what we got. Holy smokes, look at that. 55% of our audience today have been using it for longer than 6 months. 35% just a couple, and 10% are net new. So that's great. And for the 10%, I would really like to point your attention to our Wednesday webinars. If you're brand new, our Wednesday webinars are the spot to be. That's where you go and you hang out with Wayne Griffenberg. It's a live Q&A, and he does a free and personal training session, so don't miss that. We'll be sending the invites out for that as well. Here we go. This is a good one that I always like to ask. You know, what CAM software is everybody using today? Let us know. Get your votes in. Look at this.
Nice.
83% of the audience is using HSM solutions. This is awesome. This is why we do these HSM Hangouts, guys. Thank you so much for the feedback and the voting. I'd like to introduce Rob and Tim. Guys, what do you have in store for us today?
Right, so I'm Rob Lockwood. As mentioned, I'm currently employed by Oculus VR. I'm basically just here to talk about a lot of sort of advanced or particularly the multi-axis functionality in HSMWorks, and I feel like it's kind of had a bit of a bad rap that it's you know, not as functional, but I think it's almost completely unfounded. And go ahead, Tim.
Yeah, so I'm Tim. I'm just going to jump in and help out, mostly keep an eye on the questions. If I can flag some of the questions so that Rob can stay focused on showing what he has. I think he's got a good kind of handful of things to show us. So. On that note, I think Rob had just a couple quick slides he was going to pull up. Is that what you're working on? There you go.
Yep.
Perfect.
All right, so a little introductory to myself. My name's Rob Lockwood. I'm a certified level 70 master machinist. One second, let me get my notes going here. Oh, that's not the right slide. What's that doing in there?
Well, that's why you're a machinist and not a PowerPoint maker, right?
All right, exactly. All right, so some background on me. My dad is Sam Lockwood. If you're a member of the Facebook Machinist group, you probably know him. He's a moderator there. It's a group on Facebook with something like 30,000 members, which is insane to me. I would have never thought that many people online were interested in machining. But he's there. He runs a job shop, and I trained under him in his shop for a few years. He's got a few 3-axis mills, horizontal, some screw machines. I worked there for a while, and he gave me really a super good foundation. But eventually it kind of got boring because it was a job shop, but it didn't have a ton of variety and all of that fun stuff. So I moved on, and after a couple of years became a prototype machinist at a small OEM in aerospace. It was ISO 9001, all of that fun stuff. We made cargo equipment for helicopters and some aerospace stuff. Again, a bunch more 3- and 4-axis stuff, some turning. It was there during the prototype time. We bounced through a bunch of different CAM software, and geez, my phone's blowing up. And I was really being pushed pretty hard to increase throughput of our prototyping division, and we were using SolidWorks in for the engineering side. And what we found were we'd do a lot of iterations, and parts would change just a small amount, but our previous CAD software or CAM software was basically forcing us to reprogram each part every single time that a new version would come through. And it's been a few years, and I think a lot of stuff has caught up, but at that point in time, HSMWorks was just head and shoulders above. We could bring in a native SolidWorks model, have it programmed. When a change came through, it was often literally as simple as just bring in the new version, hit generate, and run the same part again. And as long as you were clean with your parametricism, even things like fixtures would update, and you could already have a program for that. And it drastically, that switch drastically increased our prototype throughput. So as I said, I'm currently at Oculus VR. I work as a model maker, and in addition to a bunch of other software, we use HSMWorks, and we're using it to program a bunch of different 5-axis machines, including a 9-axis mill turn center, a B-axis rotating head. So where can you find me online, and maybe why am I here? I'm a pretty big believer in social media stuff. Let me actually skip back to that. If you're a shop owner, a company owner, or whatever, or even just a dude like I was working in a shop and you want to improve your skills or maybe even make a job switch, the best thing you can do is be as visible as possible, and I don't think there's a better way to do that than through social media. So I'm on quite a few platforms, and I think you guys probably should be too. There's maybe some exceptions. If you're doing a bunch of ITAR work, it's probably not a great plan to be posting that up on social media, and maybe that takes some forethought, and maybe you need to figure out a different way to promote yourself. But do something. Find your way to some of these platforms. So, okay, the first place you can find me is on the Autodesk CAM forum. And if you're an existing HSMWorks, Inventor HSM, or Fusion 360 CAM user, I think you should be on the Autodesk CAM forum. It's a huge, huge resource filled with so much knowledge. It's been around since the beginning of at least HSMWorks, which has got to be 10 years now. And it's just filled with a whole bunch of super knowledgeable users. They all love sharing. They all love answering questions, fixing people's post processors, I mean. And probably the biggest benefit is that a lot of the time you can find the developers of the software on the forums who can directly answer questions and really give you sort of an in-depth how it works, or sometimes even how they can fix a problem that you're having. On there, I'm a member of the Autodesk Expert Elite program. And as you can see, I'm also a bona fide IT technician, so you can find me doling out advice like I've highlighted here, the classic turn it off and back on again, which I believe did solve the problem. So I'm also on Instagram, and Instagram is probably the best thing for machinists to come around ever, and it really doesn't seem like a logical place that you would find a bunch of machinists coalescing, but I think a lot of the creative type machinists thrive on being able to show, or I think we're all a little bit statistical and like to show off what we're working on. It also seems like about the whole Autodesk CAM team is very active on Instagram in particular. I know Tim's on there. We chat all the time. Join up.
Yeah, Rob, I'd like to pause right now and direct everybody to break out their cell phones and go pull up Instagram and follow @LockTool on Instagram right now. So do it.
Well,
We're not, pull out your phones, follow this guy. Amazing stuff. Same thing with Tim, at One Ear Tim.
that's what I was going to say. Follow Tim, follow Al Watma, follow all those guys, because you'll get so much information. Like, regardless of all the cool stuff that they post on there, that they're working on or whatever, there's tips and tricks on there all the time. It's just amazing.
I'll jump in real quick and say how it's not my natural thing to do, but I started when I started working at Autodesk, and I've been really surprised with how neat the community is and how it's not a typical online group. It's pretty neat group. So.
Yeah, and it seems like every week, half a dozen people decide to swap over to the Autodesk CAM platforms in one way or another. Yeah. And I think they're doing that because the community is so good at answering questions, and it's just something you don't find in other places. So it's really great. I also, you can find me running Locked Tool Company into the ground. I run a small company where I design stuff. I usually make one or two of them. I tell everybody I'm going to make more, and then I design something else seemingly the next week. One of these days I'll actually follow through, I swear. It's things like custom knives, custom pens, some of those you can see on there. It's fun stuff. And lastly, you can find me on YouTube doing some CAM tutorials. I try and focus, similar to this webinar, on things that are sort of on the more difficult or more intricate end. I think there's a whole bunch of people, John Groomsmo, shout out to him, John Saunders, all of those guys. I mean, there's tons more, and they tend to show something as they learn how to do it, and it's way better for beginner users than what I will ever do, because at this point I would have needed to do that 10 years ago. But what I've noticed is that there's a huge fall off where after people have learned all of the new and exciting stuff, they stop sharing the little intricate details that really make the difference between getting a super clean toolpath or knowing how something works and all of that. So I'm trying to get on there and fill it in. And I also found that myself, I learn a ton just by watching somebody else work in any software. If they're experienced in it, even if they're not talking or whatever, you can just watch them work, pick up little things. So trying to provide some of that as well. Okay, so like I said, my talk today, I wanted to talk about multi-axis toolpaths. And I think that when I say multi-axis toolpaths, I'm not talking about just 3+2 machining. I mean genuine 5-axis, or maybe we'll include 4+1. I think there's a good question here of why, or I found myself before I started using multi-axis stuff wondering when should I use them and why should I use them. And
on that question, I not to jump in, but on that question, I see pretty often people try to overuse them. They have the machine, so they want to use them, but I'll let you kind of go from there.
Right. I think that hits it exactly. Like what is the right cases to use it, and when should you use it? And there's quite a few different answers to that. Let's just go into it. My first thing would be don't. Unless it has advantages, don't try to just shoehorn in a multi-axis toolpath because, like Tim said, you have this fancy 5-axis machine and you need to use it. I would say that there is inherent risk in running 5-axis simultaneous 5-axis toolpaths that just really doesn't exist in a 3+2. And moreover, I mean, it adds volumetric error. It adds, 2 more moving axes and all of the lack of rigidity that come with that. Like I said, there's a bunch more crash risk. It's a lot more computationally taxing on everyone involved, whether you're making the toolpath, they take more effort, and also on the generation of the code, the computation time of the code, all of that stuff. So there's a caveat to that, obviously, which is unless you should, then do. Which seems obvious, but there's a reason that 5-axis simultaneous stuff exists, and if it didn't, nobody would be buying these machines or using them. So there's obviously a usage case. In my experience, I've found that it's pretty small, a very small percentage of parts that I run, I would say, require it. A lot of them benefit from it, and just about all of them wind up using something in some way that involves a 5-axis simultaneous toolpath because a certain section will have an advantage. So this is one usage case, alignment of the tool axis or edge to a geometry feature. This one I think is pretty much always covered by SWARF. There's actually another toolpath, multi-axis contour, that does sort of the opposite. And I just kind of bunch those two together. It's sort of like if a feature can be aligned perfectly to a tool axis, then this is a great option. Places where you'll see this are, like shown here, a chamfer that sort of wraps around. If in this case, you probably would just use a chamfer tool, but if it's at some funky angle or if it's changing in angle, any of that kind of stuff, a 5-axis simultaneous toolpath is versatile. It'll work right. It'll work great. It's a simple toolpath to generate, and most importantly, it's fast on the machine. It's just like contouring in 2D, only you are changing the inclination of the tool as well. I think those ones are pretty simple, pretty easy to understand how they work, when to use them. So I'm not going to go too much into that today. Another big benefit is that you can often use shorter tools by avoiding collision with the shank or the holder. This is probably one of the largest usage cases, is that a lot of the time the tool that's required to do a job either doesn't fit or just requires a gigantic length to diameter ratio and makes machining with that tool slower and ineffective. And often a little bit of tilt, as shown here. I think that tool has about 20 degrees tilt, which isn't very extreme. It is pretty safe. Would have let this tool get to an area that would otherwise require a tool probably 10 times as long. So both 3D Contour and Flow in HSMWorks have this capability in one way or another. I think one of the other reasons is to maintain a constant tilt angle. Everybody will, I would hope most people know that machining with the tip of a ball end mill is a pretty bad place to be, and once you have the ability to tilt, a lot of the time you'll find yourself doing it purely just to get a better surface finish in an instance where a surface transitions from one slope to another and crosses over sort of the tip of the tool. It's a great scenario to use a toolpath like Flow that will maintain the tilt angle and keep the tool cutting with the side of the cutter. It also will keep the tool cutting with a consistent portion of the tool, which can have some accuracy benefits as well. Probably the most common place where I wind up using 5-axis toolpaths is this usage case. It's when you want a continuous toolpath on a surface that can't be seen by a projected toolpath like your normal 3D contour, parallel, scallop, any of those. In this case here, there's a section of the surface that goes beneath. It's occluded, right? You can't see the whole thing from any orientation, but a single toolpath will cover the entire thing and machine the whole entire surface in one shot, and you'll just, get better blends and better continuity, better surface quality, all of that stuff by using a 5-axis toolpath. And again, this one's pretty easy to generate. We'll go through that one a bit. And lastly, I think this is the one that covers the should probably fall under don't, but let's be honest, they look cool. If you're doing promotional stuff, you wind up doing a lot of shoehorn in 5-axis in places where it probably shouldn't, but it is a usage case and it does do some cool stuff. There's just something about watching all 5 axes do something crazy that I think inherently strikes pretty well with everybody on here. So does anybody have any questions or comments or anything like that? Anything come up here?
I would have to say the last, I don't see any questions, but that last point is probably what drives people trying to force 5-axis toolpaths everywhere. It's because it's exciting, it's super neat. I think we have a pretty proud trade of people that like to do the cool stuff. So.
Right. It's if nothing else, it sells machine tools, maybe with bad intent, but it is effective. Yeah, it definitely falls under the don't really, but it still happens.
Yeah.
All right, so that's the end of my slide deck. I think think we can jump in and talk about some of this stuff. With all of that going on, the thing that I saw when I looked at these is that the most common, this flow comes up a lot. And this Fusion F that I did, this was an Instagram contest. It used flow entirely to surface every surface on the entire model. Flow is a toolpath that's not in Inventor HSM or Fusion 360, but I'm going to focus on it because I think that the way that multi-axis applies to flow is what makes it powerful, not necessarily the toolpath that it's generating. And my understanding is that the way that the multi-axis is controlled in flow will eventually find its way into Inventor HSM or Fusion in some way.
Yeah, to speak on that real quick, it is one of the things that's pretty high on the list that our development team's working on. I think whenever they're taking something and putting it in the Fusion and Inventor products, they're looking at it as, how can we do it better than we did in because we own the whole CAD and CAM space. They're just looking at it, how can we do it the way we want to be working with it in 20 years, not just getting it in there just to get it in there.
Yeah. Yeah, and that's definitely more important to focus on. Okay, so what I want to do is, like I said, I'm going to focus mostly on flow. We'll look at some of the other places where toolpaths, would be usable as they come up on geometry. So I have a simple flow operation, and you can see here, this is a multi-axis flow operation, and we'll look at it, and you're going to say, no, it's not, because it's not doing anything. It's just back and forth. But what it's trying to do, we'll jump into it, and it's using multi-axis, and in fact, if it wanted to, it could tilt all the way around. Obviously, we'd never want to do that. But it's a fully unrestricted flow toolpath, but it's not doing any tilting. And the question is, how come it's not doing any tilting, right? Somewhere in here, I have a great example of why it's not tilting. All right, so what the multi-axis toolpath in there is doing is it's trying to maintain normal to a surface. And in here, I have a sketch, and hopefully I can move this. This is showing the surface normal. This is on an arc. This is on an internal arc. Here's the surface normal on a spline. The surface normal on a flat surface, like what I was looking at, just points straight up. Like this is an example of this surface, or this line is normal to this surface. So what you're never going to do is on a planar surface, you will never get any true multi-axis toolpath with these controls that are available. It's always attempting to maintain normal, and the normal direction is the same as Z. It's just going to point up. What you can do, but the purpose of this being in here isn't just to show you that it's always going to point up. I think this is the best way that I could come up with to show what each control within here does. There's not really a great example. I think it's fairly easy to sort it out if you're paying attention or if you stop and think about it. But it's really easy to show it on a completely flat surface. If we add some forward tilt, we'll add 30 degrees. You'll see that the toolpath is now tilted 30 degrees. It's still a 3-axis toolpath because there's no inclination to the surface. The surface normal is constant across the whole thing. But we get that is positive 30 with forward tilt. If we come in here and we add a negative forward tilt, which is kind of ironic, you'll see it will tilt back the other direction. Pretty self-explanatory, pretty easy, right? You have another lever here that you can pull called sideways tilt. And if you look at forward tilt as being the tilt that it does along the vector or along the toolpath, sideways tilt will be the opposite direction. It'll be the tilt that happens against the normal vector or across it. So we'll toss them 30 degrees. And you have tilt in the other direction. And obviously you can use a combination of the two. We can say 15 degrees, 15 degrees, and it will be tilted forward and sideways. this is a great option for when you're just trying to maintain that constant tilt angle on a surface and keep the tool off of the tip. That's effectively what those controls are largely used for. Popping back in here, you'll get also a minimum tilt and a maximum tilt. The maximum tilt, if you imagine a cone that runs around the tool axis vector, that's how far it's allowed to tilt. To start demonstrating this, let's switch to this surface. And we'll zero these out. Okay. So because we have it completely unfettered, it's basically allowing it to tilt all the way over. It's able to go normal to this surface. And that's great. That's probably what we want, although we'd want to add some tilt in another direction to keep the tool off of the tip, right? That's one of my favorite utilities, but also a misclick. Okay, so a great example of using maximum tilt is we know this is at 45 degrees. We can start to limit that. We can tell it that we only want it to go 30 degrees. And now you'll see that it's not quite normal. It's tilted back a little bit. Yeah, I probably should have gone a little bit more extreme than that. And let's start going a little bit more. Let's get something where we have some actual tilt.
So as you click around on this is kind of a good point to talk about Inventor and Fusion. Those arrows are the reason they're working on it in those still. They're trying to get more automatic alignment. But we are pretty close.
All right, so we've reduced the amount of tilt that's allowed. And now we'll start to get some actual 5-axis tilting going on here. Right, you can see that it's maintaining normal to the surface. Flow is a toolpath that follows the UV vectors of the tool. That's important when we start talking about occlusion. Most of the other toolpaths in here are projection-based, which means that they can only project toolpath as seen from the Z-normal. Some of them have some undercutting support, but that's the basic gist of it. But we're starting to get some 5-axis toolpath. This model is not really going to give us much because there's not a lot of curvature to it. We're just sort of going to maintain normal. But I think that it does do a good example, or a good job of showing an example of how far you can go. This, I think, is actually the same thing that I used in my slide deck. By just applying some tilt and maintaining normal to the surface, you can see that we're able to tilt that tool holder out of the way. The constant tilt is nice because it's going to minimize motion at the machine, which is sort of also one of the things that you want to do if you're doing 5-axis. When you watch fancy video like my Fusion F video, that was designed to emphasize motion of the system, but in reality what you want to do is minimize it. Like I said, you always want to not use 5-axis if you can. But if you have to, what you want is the smoothest motion possible, and usually that comes from having the least amount of motion possible. But like that's pretty neat. You get a toolpath that's able to cover this whole entire surface here with a tool that's 3 times diameter. I think that's a 1/16 end mill cutting about 3 inches deep. And it could go infinitely deep as long as you don't run the tool holder or the spindle into it. But like I said, that's not a great example for showing simultaneous 5-axis stuff. Here's one that gets a little bit more going on the maintaining constant tilt. This one has probably a pretty unlimited ability to tilt, but it has a constant tilt applied to keep the tool holder off. And you'll start seeing that we'll get a really nice smooth motion. And in this case, it's maintaining the forward tilt, but going both directions. In reality, what that does is it gives you lead tilt in one direction because we're tilted onto the front of the tool. But when it heads back in the back direction, you have lag tilt. and you probably wouldn't really want that, so you'd want to swap to using a one direction instead, and probably go on the shortest path. And that way we'll get lead the whole time. And this, I think, is a great example of HSMWorks Toolpaths just doing a great job. That stay-down linking right there is really pretty fancy. In this case, the vector in and out is pretty similar, but it's purely just because of where I ended the surface. It's oftentimes neat to get ones where the vector changes, and you'll see that it smooths the tilt out over the entire move, which is pretty tough to do. But it really makes for a nice, clean toolpath versus some other stuff will wind up retracting to a different location, correcting the new tilt, going back in, and it's a much slower and just kind of looks more amateur. I don't think we need that one much more. There's not a whole lot to see there. This is eventually we're going to get to doing some stuff on that one. I think we need that. Okay, so this is starting to get into some of the more real-world examples here. I used this one. Let's take a look at what would happen if you tried to do this three-axis or 3+2. It's going to have some issues. So first, let's just try and toss a parallel toolpath onto it. And nothing that we do is going to get this to drive down and onto this section of the surface below. You can see that there is undercut here. It's just not going to do it. The tool isn't capable of doing it from a single orientation. And even if we change that orientation, this is one of my favorite tips. If you're running SOLIDWORKS 2015 and you're doing a lot of 3+2 work, there's this awesome feature that they put in that lets you create a plane purely based on a view. And all you have to do is select a point and select here, create plane parallel to the screen. This is entirely not parametric, so it's, I mean, you can update it, but it basically is just going to create a plane based on how you're looking at a model, which we'll go into some more, hopefully some more useful stuff with that. So then you can use that plane to drive your tool orientation. You can see that it just picked the vector normal to how my screen was looking. But obviously, from any one orientation, you're not going to get complete coverage out of a projection-based toolpath on this. It just isn't going to happen. Therefore, I'm fairly confident that aside from using a T-slot cutter or a lollipop, multi-axis toolpaths are probably the only way you're going to machine this entire surface in one shot from one, I shouldn't say orientation, but I'm going to from one orientation. And that's because flow is not based on a projection. Rather, it's based on the surface normal, right? So because of that, it can project in places that it can't see, or it can generate toolpath in places that it can't see. This is a super, super simple toolpath. It's in here. The only settings that are being applied is a maximum tilt of 60 degrees, which is probably overkill. But that's just giving it just enough so that it will tilt past and be able to see, or be able to get the tangency of the tool out of the way. Yeah, like I said, it's way more than we need. But it gets the tangency, the shank of the tool or the fluid of the tool out of the way so we can continue surfacing. And you'll see it. It's able to cover the entire surface with a single toolpath. This is a good example of where the maximum tilt comes into play. If you can imagine the surface normal on this, specifically this section right here, it's pointing the tool way down, way into the negative direction. If you had a vise or a table, which you do on your 5-axis machine, your tool holder, if it maintained normal and was pointing in that direction, let's take a look at what happens there if you do it. So we'll just open this all the way up, and we'll say allow it to go negative. And we'll probably actually get some really crazy, oh, we didn't, okay. Sometimes you'll get some crazy stay-down linking moves that want to go underneath. It's funny to me that the default is 180 degrees on multi-axis flow because there's like no applications for you. But you can see right there, this tool is pointed massively negative. In this case, I guess it might be okay. That's probably within what I think most 5-axis machines will give you about negative 100 degrees or so. I think 120 is about the max I've seen. And that's because everything, your table starts getting in the way, and we'll look at that when we get to some stuff that has a vise and some machine simulation. But so you just really don't want it tilting that far, but you do need to control the tilt so that it can get past and access that occlusion. So that's where controlling the maximum amount of tilt is really important. We'll try and hit the minimum amount that we need here rather than just some. Yeah, there you go. So that's much better. It's tilted enough to keep the tool holder out of the way. It's tilted enough to keep the shank off, and it minimizes motion. So that's probably enough time spent on that one. Okay, and this is probably a really common real-world example. This is a part that I made that mimics something that I've done before, and it has these bosses that sit down along some pretty deep vertical walls, and you probably could do this mostly 3-axis if you had a T-slot cutter, but and we're planning on undercutting this and surfacing it from the top. But as you can see, there's some draft to this surface. Hopefully that's apparent. So there's some negative draft there. And if you were running a T-slot cutter around here, it's the one that's small enough to reach into this corner isn't going to have enough neck to reach down in here, right? It's going to shank out, and the shank would rub here. I probably should have actually built an example of that, but I didn't. And it's interesting, got an adaptive toolpath. If you just look at a typical flow, it's actually not going to work either. You've got, because we're maintaining normal to the surface, it wants to tilt over, and eventually, the surface normal from this is that it points off in this direction towards this wall, and it's going to run into it. So that's not great. We can't have that. In addition, here's just a normal 3D contour operation, and it generates great, and it's a pretty clean code, but it's not going to generate the undercut with a ball end mill. And so that draft doesn't get seen. Right now I don't have any collision checking on, so it's also running right in there. We can overcome the fact that it's running into the surface, but nothing that we do will allow this to tilt the ball over and get it to contact here. It's always going to generate these paths, but with tilt. I think I have an example of that. So this has automatic collision avoidance turned on, whatever they call that, multi-axis tilting collision avoidance, which uses the shaft and the holder to automatically tilt. This is super useful. This is just a usage case where it's just not going to work. Because as you can see down in here, the passes aren't able to undercut it. So this is where you start having to sort of combine the different parameters in here to get something that will work. This is totally machinable. Oh, and I should also say this is actually a great candidate for a swarf machining operation normally, because it is a planar or a conical surface, so it does have an axis that can be aligned to a straight tool. We'll actually generate one here real quick. I think I have a tool. And we'll see maybe some of the problems with why you maybe wouldn't. So the toolpath itself is pretty good. It's actually it's really great. It's going to it basically perfectly aligned with this starting edge, and I did absolutely no configuration on this at all. I just built this up, and it's perfectly tracing. I don't know if you can see that. It's perfectly tracing the fillet. In this case, I did a good job selecting the tool because it's smaller than the surrounding radius, so it doesn't gouge. It's going to trace that perfect. But I'm sure everybody saw what happens right here. And that's just not going to work. We could use a much longer tool, and actually I think it would work. But this is kind of the culmination of all of those things in the slide deck, right? We want to use a shorter tool. We want to be able to machine a surface that's occluded from different views. and some of the other options don't work. So let's take a look at this flow toolpath. I think we can tweak it to get it to work. Basically what we need is for this toolpath to not run into this wall, right? Otherwise it's great. It's not shanking out. I've got enough tilt already. It's contacting all the way down because it's flow and it generated those toolpaths based on the UV of the surface, and it's good otherwise. It's just it wants to tilt in the direction we don't want it to. You have some handles that you can pull in here. We already have our maximum tilt, and that's probably what we want. We could apply some sideways tilt, but as viewed from the top, that sideways tilt is already being limited by our maximum tilt. That's the same handle, right? Our passes are running this way, so our tilt wants to tilt this way. Our actual tool, our normal to the surface, is coming off of here in the negative direction. So we're already massively modifying that. We're only allowing it to go 20 degrees, so it's way tilted. You could use forward or backward tilt, but in either direction, if you tilt it forward from this direction to get rid of the clearance here, it's going to cause you to have more interference on this side, right? So say we add 15 degrees. So we probably got to where, maybe I didn't get it enough. So we're to a point where we're clear there, but now we almost immediately have collision on this side. Right, we have more collision over here. So what can we do? None of our handles work, right? Well, the thing to keep in mind is that all of those handles are based off of the initial vector, your frame or your WCS or tool orientation, whatever you want to call it. Those handles are based off of that normal. So I already prepared a plane here that's tilted about 20 degrees. If we instead base those handles off of that surface, what it will do is have the effect of tilting everything away from that wall towards this wall, so we still need to watch and make sure we don't get a collision over there. But now you'll see we're clear. Oh, and you know what? I made a boo-boo though I forgot to get rid of. And yeah, I just said I made a boo-boo. What? Okay. So now we're tilted away from that wall. We're still clear down here, tilted away from that wall. Let's go all the way to one of these end passes and make sure that we're not tilted over too far. Right, so by doing that, the thing to keep in mind here is that you can control all of those handles, even if some of them are being maxed out. Your initial tool vector has a whole lot to do with how that cone allows movement to progress. Right, that cone that the minimum or the maximum tilt is allowing is entirely based off of that Z vector, off of your tool orientation vector. So keep in mind you can use that to tilt everything in directions that otherwise you just don't have the handles for. Let's see. Let's get rid of this draft so that I can use this as an example for a 2D contour. Looks like somebody was asking about that. So, let's get rid of this guy. Okay. Like this. All right, so I'm going to use automatic tilting and go through some of that on this, the tool shank and holder avoidance. And to do that, you have to keep in mind that it is checking against both the model and the in-process stock. So if I did this without an operation here to at least remove all of the material first, we just wouldn't get any good results. So we have to have something in there. Okay, so this is a fairly clean toolpath that we've got going on here. It's just a 3-axis 3D contour, but obviously it has some problems. There's going to be tons of places where the shank is rubbing or just plain colliding. And also I think if we jump way later in here, eventually we get some tool holder as well. So that's bad. We don't want that. Let's take a look at what happens if we just enable it and we'll give it, already got it in there, 30 degrees maximum tilt. These toolpaths take a little bit longer to calculate because there's a whole lot going on there. What it's going to do is it's going to take my existing toolpath, look at every place where it's contacting, start applying tilt to it until it gets rid of a collision. Oh, and I totally just skipped over a section. Here, while it's calculating, we'll pop in and take a look. I think these were already set, but when you enable multi-axis tilting, it's going to automatically enable shaft and holder avoidance. And what you have to do here is put in a number or a distance that you want to keep clear from stock and from model. And the shaft is going to affect anywhere along any of this black section. It's basically going to take and offset that by some amount and only allow that amount to get close to the model. And same deal with the holder. It's going to take everything that's blue. It's obviously pretty important if you're using these that you have a shank accurately defined, you have a holder accurately defined, you have the distance from the tip to the end of the tool holder accurately defined, especially when you start getting into small numbers here. Your intuition might tell you to throw a pretty big number in here, and the thing that's going to do is not help you because the toolpath needs to find a solution, and the larger these numbers are, the more tilt it needs to use to find a solution, and the more likely the solution that it finds is going to be bad because it requires too much tilt. And again, we want to minimize motion. Okay, so these settings, I think they're probably pretty good. It might be a little close, but this is a small holder, and it's fitting into some small places. All right, so we've got some tilt here. You can start seeing the vectors off. You can also see there's some areas that it wasn't able to find a solution for. It trimmed some passes because it probably has a nice warning in here. One or more passes were split due to given shaft/holder. And that's basically just saying this pass, it originally was continuous. The shaft and holder don't fit in there, so, or at least with the current settings here and the current allowance here, it can't find a solution. Let's take a look at what it did do. So now it's automatically tilted for me. Oop. Here, let's slow this down and jump to this pass. So it's keeping that, right now it's clearly being driven by the shaft and avoiding collision there. It's maintaining, even though there's no risk of the shank colliding here, it's maintaining that tilt to provide you with a nice smooth toolpath. What you wouldn't want to have it happen is just add extraneous motion here to correct the tilt and then have it tilt back when it gets done. So I think the logic here is that it goes along, finds a solution, and maintains that solution until that solution doesn't work anymore. Let's continue. It's doing a good job. It's maintaining. You see there, it starts wanting to glide again. As it gets down in here, we can look at it and probably figure out. Looks like the combination of the amount that I'm letting it tilt and the amount of, basically the length of the actual tool are preventing it from getting in here. So maybe we can try swapping out to a different tool. That one looks good. This one's got a lot more length there. See if we can't get the whole surface. And so even if this works, one of the things that I don't like is that it will be adding motion in places that we don't necessarily need motion. It's going to add some tilt sort of prematurely. You can see that the first passes, I mean this tool that we've got can make it quite a ways without needing any tilt at all, right? It's not seeing interference for quite a while. But what you'll see is that it's immediately adding some tilt. And that might be what you want. To me, I usually try and keep it 3-axis until I need to swap over. And there's a great way to split it off. It did finish generating. We did get Toolpath that's able to reach all the way down in there. It's doing an awesome job. But let's look at how you can split that up into 2 toolpaths and just have one with multi-axis tilt. So what we want to do is disable multi-axis tilting, but we still want to keep shaft and holder turned on, and we're going to trim. So we've got a toolpath that's generated. I probably would want to tweak, let's tweak some settings real quick.
Yeah, that trim feature is a good feature that I probably don't see used enough. That's a good example of it.
Yeah, so you can see here it's being trimmed by, as it gets too close to the shaft and holder, that's clearly the last toolpath, or the last level that it can do before it would start having some collision. So it's just getting rid of the extra passes. So then what we can do is go into this one, which is the exact same toolpath, but it has multi-axis turned on. But what we want to do is use rest machining. Probably put a slightly smaller value in here. Same thing here. We'll turn on plunge. And this will just go up and clean up in the areas that you need the tilt, that you genuinely need the tilt, and that they're basically impossible to do with that tool without tilting. This will come in and get those spots. And this is, again, like I said, if you don't need to use it, the computational requirements go way up when you start doing these types of calculations. You can see how fast this toolpath calculated, and it's pretty intense too. It's checking everywhere that the tool's colliding, but things just slow down, and that's not anything on HSMWorks. I mean, it's by far the best in HSMWorks. It's just a fact of the matter that the computational requirements go way up, so your toolpath takes way longer to compute.
Yeah, it's easy to think about, everything that has to happen, especially with rest machining and tilting. It has to take into account everything that's to happen before and then start tilting. So that's a good example right there.
Yeah. So that one, now you can see, it does look like it drops some passes in here. It's not quite getting in there. That's most likely just due to rest material adjustment. If I wanted to tweak that value and wait for it to generate a few more times. But you can see this is a pass where it's not using any tilting. And we'll jump to the end where it starts using the tilting. It's going to come back in and just clean up those areas using tilting where it couldn't otherwise reach it. This is among my favorite of tricks because it really produces great results. It looks like we're starting to get low on time here. I want to make sure that I'm leaving any questions and stuff. I can't. Have you got any interesting ones, Tim?
Yeah, we'll follow up with some of the questions. One question was, can you use check surfaces in Flow?
No, Flow is entire. So the answer is no, but Flow is constantly checking against adjacent surfaces anyway. So if the tool starts running into it, it shouldn't gouge.
Exactly. Yeah.
To be entirely honest, I have had a few instances where it will. I probably should report those to development, but in theory it shouldn't. It's always checking. It's either limited by the boundary of the surface or limited by surfaces that it runs into.
Yeah. I think any questions we're missing, I'm scrolling through them, but any questions we miss, we'll follow up with answers. I know you had, we are coming up on time, but I know you had another example. Did you want to get over to that before we're done? There you go.
So we've got this guy. I don't really have anything in particular that I wanted to do on here.
Gotcha.
I think this is probably the clear surface of where multi-axis would be a winner here. I think most everything else is probably 3+2 capable, maybe with some advantage to some 5-axis stuff in some places. This is probably starting to get to where you'd maybe want to use a tool that's tilted. Maintaining some tilt on some of these clean surfaces would probably be a good idea. But this one here, you just can't really do that any other way. It's occluded from the top. Any orientation, can't see the whole surface, but it's going to be a great candidate for Flow. Again, we'll just, and actually I think this should be a good example of it, hopefully avoiding collision or avoiding running into adjacent surfaces.
Okay.
So we'll go to about 35 degrees. We'll tell it to produce about 100 passes. We'll select this guy. Oh, and we need a tool, of course.
I'm getting one more question. If you have any examples of where multi-axis contour is a useful tool.
I have never actually used that toolpath. It's possible that it's a little blind spot for me, but I don't have any examples at all of when.
I've seen it forced into a couple situations, but it's generally not my go-to.
Right. Yeah. I could maybe come up with a convoluted example.
Yeah. Yeah.
But I'd love to talk to whoever implemented it and see why.
Honestly, I think they had bigger plans for it and then started heading in a different direction with some of the toolpaths that haven't been seen yet. So, yeah, that's probably the best answer.
So this is seeming like it's taking me forever to generate. One of the neat things is we can jump in here and start taking a look at it. Even while it's generating, it hasn't generated any leads yet, and you can see it's clearly doing some multi-threading because it's generating passes non-linearly. So it's using all of your cores to generate some stuff. But you can see it's not going to run into that wall, even though the surface normal would cause it to run into that wall. So that's a good example of where you don't usually need check surfaces. It probably would be nice to be able to give a little bit more, and I could make an argument for that being implemented, but I don't think that it's a easy thing to just toss in there. So, but you're getting some nice multi-axis. We're staying away just based on that tilt. It's generating all the way around the surface. So maybe it's done at this point. We're 99%.
Yeah, I think it's important to note, this part you've already said, but it's a really good candidate for a lot of 3+2 and then a handful of true 5-axis toolpaths. We got a buddy that worked at a major auto manufacturer, and he had access to everything you could dream of, and often he said, in the end, he often got better surface finishes, programmed faster, made parts faster with 3+2 machining. This is a perfect example of when you would want to go to a flow 5-axis toolpath.
And here we'll just toss this sucker into machine simulation. So take a quick look. Make this thing in place. Hop back into simulation.
Probably also worth noting that right now machine simulation is only in HSMWorks. Some workarounds I've seen people do successfully for Inventor if you're really just looking for collisions, you can model your tool holder up kind of as your whole spindle. That's a good workflow when you don't have machine simulation.
Right, and I should add, even SANS, or even if you do have machine simulation, that is a very, very useful trick.
Yeah.
The reason is that then you can use the entire spindle to check in Toolpath.
Yeah.
So then your Toolpath can avoid your spindle rather than just finding out that it's going to crash and then not having any way to do anything about it in the Toolpath. Yeah,
we did a demo about a week ago where we had a multi-part Raptor fixture that the spindle was 80 thousandths from another fixture, and I did all that simulate verification with just modeling up the tool holder as the whole spindle, and it was I comfortably knew it was going to miss by that amount.
Right, and by the same token, you also can add, I should have maybe shown that, you can add fixturing. Sometimes I'll even add that into the model to avoid running into it. But you can also define fixturing and really do a pretty decent job even without machine simulation. It's great to be able to see how machine components are going to interact directly, but I don't necessarily think it's a necessity.
Well, great. We could obviously do this all day, but we're coming up on the hour, and I think we got enough good information for the hour, and I wanted to thank you for your time. I know you put some pre-work into this, and hopefully turn some people on to what we can do.
Yeah. And on Instagram, there's this hashtag people are using that's "Fusion is not a toy." I also think that same thing has been attributed to multi-axis toolpaths in HSMWorks. I don't think anybody would argue that HSMWorks as a whole is a toy. It's probably one of the most powerful CAM out there. But hopefully this goes a ways to dispel that in all aspects of the program.
Yeah, great stuff. Thanks for your time, and we'll hopefully see you again soon.
Yeah, thanks.